Hello everyone. Let me ask you something curious. Have you ever tried to imagine shrinking a solid object like a cube down, first to just one of its flat sides, then only to its edges, and finally down to just a tiny dot? That's exactly the kind of abstract thinking Euclid used more than 2000 years ago. Geometry, after all, is built on the journey from solids to points. A solid has length, breadth, and height. Its boundaries are surfaces. A surface has only length and breadth, and its edges are lines. A line has only length, no breadth, and its ends are points. And finally, a point has no part, it's just position, no size at all. That's the beautiful hierarchy: solids, surfaces, lines, and points. Have you ever wondered how everything we study in geometry begins? It all starts with some of the most basic and essential definitions that lay the groundwork for the rest of the subject. Today, we are going to explore the fundamental definitions from Euclid's elements, which are like the building blocks of geometry. Let's begin with definition 1. A point is that which has no part. It's something you can't physically touch or measure, it's just a location in space. Imagine a tiny dot on paper. It doesn't have any length, width, or height. It's simply a position. Moving on to definition 2, a line is breadless length. It has length, but no width. It extends infinitely in both directions. Think of a road that stretches out endlessly. The ends of this line, however, are points marking where it starts and where it stops. Now, definition 3 tells us something important about the ends of a line. The ends of a line are points. Even though a line seems infinite, we can always define its start and end using points. These points give us boundaries even in an infinite world. Next, let's dive into straight lines. A straight line lies evenly with the points on itself. Imagine the edge of a ruler. It stays perfectly straight, and the points along it are perfectly aligned. This definition is about the consistency of straight lines. Definition 5 introduces surfaces. A surface is that which has length and breadth, but no depth. It's flat, like the surface of a piece of paper or a table. These surfaces have no thickness, they're just the area defined by their length and width. Let's talk about edges now. The edges of a surface are lines. If you trace the boundary of a surface, you'll find lines that outline its shape. Just like the edges of a piece of paper, these lines mark the limits of the surface. Finally, we arrive at definition 7. A plane surface is one that lies evenly with the straight lines on itself. Picture a flat table. It's a plane surface because any straight line drawn on it will lie perfectly along its surface. There's no bump or curve, just a perfect, smooth plane. And that's our introduction to some of the most basic but essential definitions in geometry. These are the first steps in understanding more complex geometric concepts. In the next scene, we'll start combining these elements to explore shapes, angles, and much more. After definitions, Euclid introduced axioms, obvious universal truths. Let's explore them. Axiom 1. Things which are equal to the same thing are equal to one another. Imagine if the area of a triangle equals a rectangle and that rectangle equals a square, then the triangle equals the square. Axiom 2. If equals are added to equals, the wholes are equal. Axiom 3. If equals are subtracted from equals, the remainders are equal. Axiom 4. Things that coincide with one another are equal. Basically, if you place two shapes on top of each other and they match exactly, they are equal. Axiom 5. The whole is greater than the part. And axioms 6 and 7. Doubles of equals are equal and halves of equals are equal. These statements are so natural that we use them without even noticing. They're the invisible glue of mathematics. Now, Euclid moved to postulates, assumptions specific to geometry. Postulate 1. A straight line may be drawn from any one point to any other point. Today we write this as, through two distinct points, exactly one line passes. Postulate 2. A terminated line or line segment can be produced indefinitely, in other words, extended forever. Postulate 3. A circle can be drawn with any center and any radius. So pick a point, fix a length, and you have a circle. Postulate 4. All right angles are equal to one another. That's why we never argue about whether one 90-degree angle is more 90 than another. Postulate 5. The famous parallel postulate: if a line falls on two lines and the sum of interior angles on the same side is less than two right angles, then those lines meet on that side. This one is far more complex than the others and later gave birth to non-Euclidean geometry. Welcome. Let's dive into a fundamental concept of geometry today. Have you ever been in a situation where you're laying out furniture or setting up a workspace and you want to figure out how different sections relate to each other? It's like knowing that the distance between 2 points can be broken down into parts, and when you add those parts together, you end up with the total distance. Sounds simple, right? Well, that's the power of this simple axiom in geometry. So, here's the setup for today's problem. We are given that points A, B, and C are collinear, with point B lying between A and C. What does that tell us? Well, in simple terms, this just means that A, B, and C are all on the same straight line, and we are told that B is somewhere between A and C. Imagine a line with 3 points marked on it, A, B, and C, like dots along a ruler. Now, our task here is to prove that the sum of the lengths of AB and BC is equal to the length of AC. Mathematically, we are trying to show that A plus BC equals AC. How do we do this? Let's break it down step by step. According to Axiom 4, which states that things which coincide are equal, we can use this principle to help with our proof. Axiom 4 tells us that if two things line up perfectly or coincide, they must be equal. So, here, since AC coincides with the combination of AB and BC, it's clear that the total distance from A to C is exactly the sum of the distances from A to B and B to C. Hence, we can say that A plus BC equals AC. This is a direct application of Axiom 4, and the axiom justifies why these lengths are equal. Quick insight: the idea behind this axiom is simple but profound. It's all about coincidence. When two segments of a line exactly overlap, they are equal. This principle helps us in a lot of geometric proofs, whether we are working with lengths, angles, or even shapes. So, next time you're laying down measurements or calculating distances between points, just remember this axiom: when things coincide, they are equal. Geometry is really that straightforward. And that's how we use basic axioms to understand the relationships between geometric points. In the next video, we'll explore more about straight lines and how they connect to different geometric figures. Stay tuned. Have you ever noticed how, no matter how many times you try, two distinct roads can only cross at one point? That's the same idea here with lines in geometry. Lines, no matter how far they go, can only intersect at one unique point if they intersect at all. Let's break it down. We are given two distinct lines, line L and line M. Now, imagine these lines are not parallel, they do intersect. But here's the catch. Suppose they intersect at 2 points, let's call them P and Q. Hold on a second, P and Q are just 2 points. Could there possibly be two lines that pass through these exact same 2 points? No way. This is a contradiction. Why? Because of a basic axiom in geometry that says, given 2 points, only one line can pass through them. It's as if the universe of geometry has decided, no, you can't have two different roads intersecting in more than one place. This is a one-of-a-kind crossing. Hence, what we've shown is that two distinct lines cannot have more than one common point. The intersection is unique. You cannot have two distinct lines passing through the same 2 points. That would violate the uniqueness of the intersection. Quick insight. See that contradiction? It's like when you hear someone claim two different roads can intersect at the same place twice. It just doesn't make sense, right? In the same way, we've proved that the intersection of two distinct lines can only happen at one unique point. And that's how we prove the uniqueness of the intersection of two lines. Next time, we'll dive deeper into other properties of lines and intersections and explore how they help us understand the space around us. Stay tuned. So, what did we learn today? Geometry stands on a few undefined terms like point, line, and plane. Euclid built his system using axioms, universal truths, and postulates, geometry-specific assumptions. With these, he proved examples like a plus BC equals AC, the construction of an equilateral triangle, and the uniqueness of lines. This method of deductive reasoning, starting from accepted truths and building step by step, is what makes mathematics powerful. And that's the foundation of Euclid's geometry. In the next video, we'll see how these postulates, especially the fifth one, open doors to entirely new branches of geometry.